You know, we can produce all sorts of angles within circles using chords and radii and so forth. And it turns out that there's so much structure to the symmetry of the circle that we can actually gain a great deal of insight about these various angles. Let's talk about inscribed angles. Now, first of all, what's an inscribed angle? Here's one version of an inscribed angle. It basically is just taking two chords that actually share an endpoint in common. And the angle that's actually between those two chords is called the inscribed angle. Let me show you a few examples. So here's an example. Here's another example. Again, you see two chords. They share the same endpoint. And this angle right here is called the inscribed angle. Let me show you another example. Here again, you see two chords. They share a point in common, endpoint. And you can see that this angle right here is an inscribed angle. So you can notice a couple of things. First of all, it's okay to have one of the chords actually be a diameter. That's completely fine. Remember, a diameter is a very special example of a chord. It's okay for the two chords to contain the center of the circle actually inside of that angle. That's fine. Or not. In fact, they could actually, you know, sort of have the center be off on the side. Any configuration of that kind is completely allowable. Now, here's a question. How can we find the measure of the inscribed angle? Well, again, the circle is so spectacular that it wouldn't have it any other way but to have the formula be really beautiful. This angle measure is somehow connected to this measure of this arc. And what is the answer? The answer is given by the inscribed angles theorem, which says that the measure of the inscribed angle is 1/2 the measure of the arc. So if you find the measure of this arc and take half of it, you actually get the measure of this angle. If you take the measure of this arc and take half of it, you get the measure of this angle. If you take the measure of this arc and take half of it, you get the measure of this angle. It's absolutely amazing. What a beautiful, beautiful theorem. Let's take a look at some examples where you can see this theorem really proving its true colors. So here's a neat picture. Got a circle, got a whole bunch of chords. Let's have some fun. We're given that the measure of this arc is 80 degrees. Remember, the measure of an arc is given in terms of degrees. Okay? We're also given that this inscribed angle formed by this chord and that chord is equal to 50 degrees. And our mission, should we choose to accept it, is to find the measure of angle CDB. CDB. So that's this measure right here, this angle right here. But that's really easy because you can see that actually is the inscribed angle associated with this arc. Well, since this is 80, we can actually figure out what the measure of this angle is. It's just half of 80. Half of 80 is 40 degrees. Isn't this cool? I mean, it's so beautiful. There it is. That's 80. This is 40. Bang. Okay. Now, we're told that this angle has a measure of 50 degrees, and our final challenge is to find the measure of the arc AD. AD. We want to find the measure of this arc. What would it be? Well, wait a minute. We have this formula. This is an inscribed angle for these two chords. And since that's 50, and that's going to be half of the measure of this arc, then what must the measure of this arc be? 2 times 50, or 100. So this equals 100 degrees, and this we saw equals 40 degrees. It really is a beautiful result that allows us to quickly connect angles with arcs. Absolutely beautiful. I love it. Circles are great. Let's take a look at some consequences of this really terrific inscribed angles theorem. So look at this. Here's a circle with lots and lots and lots and lots and lots of chords. Let's take a look and see if we can parse this really carefully. I want us to focus on angle C. Well, technically, I guess it's angle ACB, but I'll just call it angle C. So I want us to focus on that angle versus the angle D versus the angle at E. Now those angles are all over the place and they all look sort of unrelated, but let's think about those angles for a second. Well, notice that that angle is actually an inscribed angle because it comes from these two chords. And notice that actually those two chords sort of span out this particular arc. So we could actually find the measure of this angle by taking the measure of this arc and taking half of it. Okay, fine. But now look at this angle. That's also a different inscribed angle, and that inscribed angle actually comes from these two chords, but notice those two chords actually capture the same arc. That means that the measure of this angle is going to be equal to 1/2 the measure of this arc. So what about the measures of these two angles? They're equal because they both have captured within them the same arc. What about angle E? Well, that's an inscribed angle that actually comes from the same arc again. So the really cool thing is the way these are drawn, we see that the measure of angle C is equal to the measure of angle D, which is equal to the measure of angle E. And so by a theorem, we know that all these angles are congruent. That is a really cool fact. And actually, a wonderful consequence of this theorem, which actually has some utility. Let me show you how practical this really is. Let's suppose that we were playing Chinese checkers. And all of a sudden, we had this hankering for figuring out angles, right? So we stop the game, hold the game for 2 seconds, and let's take a look at what we've got. So suppose that when we measure, we see that, in fact, this little angle right here this inscribed angle is 50 degrees. And suppose that we know that this arc, RS, is 110 degrees. The challenge for us, before we return to our game, is to see if we can find the measure of angle QZR. So our goal is to figure out this angle right there. And again, it's one of these questions that I really like because it seems like it's impossible. But let's take it slowly. Okay, now, what do we know? Well, I know that since this is an inscribed angle, I can actually figure out the length of this arc. Why? By this formula. Because the angle is going to equal half the arc measure. So if this is 50, then this must have been 100. So I see that this measure is 100. Well, but wait a minute. This also is the arc associated with these two chords and this particular inscribed angle. So what does that mean? It means that the measure of this angle must be half of this, 50. So if this is 50, that tells me that this must be 50, and that was the principle we just saw. So in fact, this angle right here is 50 degrees. I'm looking for this angle. Notice I've got a little teeny triangle here. I know this is 50. I want this. Oh boy, oh boy, oh boy, oh boy. If I could figure out that angle, I could use the fact that the sum of the angles of a triangle equal 180 degrees. I'd be home free. Is there any way for me to find that angle? Well, how's that angle formed? It's formed by this chord and this chord. Hey, wait a minute. That angle right there is an inscribed angle. Here's the arc. Whoa! And that arc we know is 110. Yes! Because since that's 110, I can plug it in and find the measure of the angle. It's going to be 1/2 of 110, which I happen to know is 55. This is 55 degrees. I've got a little teeny triangle here, and I know two of the angles, 55 and 50. And so if I add up 55 and 50, what do I see? I'd see 105. I know the total sum of the area of the angles is going to be 180, and I have 105, which leaves how much for this angle, the angle I want? That angle must be 75 degrees. And so the measure of angle QZR equals 75 degrees. Look at the great power of this wonderful inscribed angles theorem.